In this video, we're going to be looking at electron configurations, which in a way is kind of a summary of what the quantum numbers tell you, but in a much more concise and clear way. So when we think about electron configurations, quantum numbers are very specific and detailed. You can think about quantum numbers as kind of a very zoomed in, super detailed, very specific set of information. If you look over on the right hand side of the table, this is what we generated when we did quantum numbers in a previous presentation. You almost look at that, and if you look at that table and you didn't really understand what was going on at first look, it kind of looks like computer code. There's a bunch of ones and twos and negative ones and threes, and it's very detailed and very specific. Sometimes what we want is a less detailed summary of information. What we're going to see is that electron configurations provide this zoomed out summary. Quantum numbers and electron configurations get at the exact same information. The quantum numbers get into the specifics while the electron configurations provide the summary. One kind of way of thinking about this is, we talked about sometimes the quantum numbers can look like a set of computer code. Well, if we kind of use that analogy a little bit further, it kind of makes sense. When you look at those quantum numbers, that's like looking at the computer code. That's the real details. When you're doing electron configurations, you're not looking at the details of the code. You're just using the information that the code is providing. So that's that kind of zoomed in, zoomed out approach, that the electron configurations are giving us that zoomed out, while the quantum numbers are those zoomed in, detailed specifics. So I'll show you how to write electron configurations, and this is going to be very similar to what we did with the quantum numbers. I'm going to look at the first 10 elements. I'm going to look at 10 electrons in here, and then we're going to do the electron configurations because we have to be able to relate this to the quantum numbers. So you may want to look back at that quantum number table that we had. That first electron in the quantum number table, we had N is 1, L is 0, M sub L is 0, M sub S is plus 1/2. Well, what does that really mean? The electron configurations tell you kind of what that means without kind of the crazy code. So if I look at the electron configuration column first here in the middle for hydrogen, what those quantum numbers really mean is that I have one electron in the 1s orbital. 1s1 is its electron configuration. The superscripted 1 tells me I have one electron in that s orbital, and the energy level is the first energy level. What we also sometimes write are orbital diagrams as well. So a little bit more of a pictorial way of seeing the electrons. And sometimes that can be useful in bridging the gap between electron configurations and quantum numbers. So the orbital diagram for hydrogen is one electron is we use boxes to represent the orbitals, and we label the boxes. We would have one electron, that's what the arrow represents, living in a 1s orbital. This represents the same information, whether you do it, kind of highlighting that in blue, whether you do it with the orbital diagram or the electron configuration, it means the same thing. There's one electron that lives in a 1s orbital. Then you're just kind of following that building up approach that we saw the same thing done in the quantum numbers. Now we want to put in another electron. Well, where does that electron go? Lowest energy state possible. There's still room in that first energy level, so my electron configuration for helium is going to be 1s2. If we look over on the left with the orbital diagram, now I have two electrons in that orbital. The spin, one spinning up, one spinning down. Remember, same orbital, those spins have to be different. Now you can kind of see I don't have any more room in that orbital. I have to go to the next orbital. Well, kind of build up where I left off. Lithium with 3 electrons, I start off where I left off. 1s, I can't fit a third electron in, so I got to find the next orbital in energy. That would be the 2s orbital. So the electron configuration for lithium is 1s2, 2s1. How does that look like in the orbital diagrams on the left? Well, I still have those 2 electrons in the 1s. Now my next energy orbital is this 2s orbital. And I have 1 electron in there. Now I just build up from where I left off at before. Do I still have room in that orbital? Yes, I still have room. So I want to make use of that room. So when I get to 4 electrons with beryllium, 1s2, I still have room in that 2s, 2s2. How does that look with the orbital diagrams? 2 electrons in that 1s orbital, 2 electrons in that 2s orbital. Now when I get up to 5 electrons, I no longer have any room in that 2s orbital. So if I get to boron, which has 5 electrons, 1s2, 2s2, I can't put a 3rd electron in there. I got to go to the next orbital. Now I start the p's, 2p1. Now here's where your orbital diagram looks a little bit different than what you would expect. We see the 1s and the 2s, but now if I highlight this in green, the 2p's, notice we're looking at there's 3 different boxes here. Why are there 3 different boxes? There's 3 different boxes because remember there's 3 specific p orbitals. And notice how these boxes are all touching each other in green. If the boxes are touching each other, what that means is that those orbitals have the exact same energy. If boxes are touching, they have the exact same energy. All 3 of those p orbitals are identical, they're just along different axes. We don't have the 1s and the 2s orbitals touching, or the 2s or the 2p orbitals touching, because there's an energy gap here. Between 1s and 2s, that's an increase in energy. We're not going to have those touch. Between 2s and 2p are a little bit higher energy. We're not going to have those touch. But the 2p's, those are the exact same energy, so those are going to be touching each other. I have 3 of them. Doesn't matter which one I put it in, but you can see that in the green. When I go up to carbon with 6 electrons, now remember we talked about this with the quantum numbers, but here you can see it again. I know where the first 5 went, 1s2, 2s2, we saw where the 5th one goes, but now remember, I don't want to pair these electrons till I have to. Why? Because each one of these specific p orbitals has the same energy, so I'm not going to pair it until I have to. I'm going to put it in a different p orbital, but I'm aligning the spins for my configuration of 1s2, 2s2, 2p2. If I go on to nitrogen with 7 electrons, I have 1s2, 2s2. There's still room in these 2p's, so 2p3. Well, we see where the 1s's go, 2 in the 2s's. Now, here's where I'm at with 6 electrons. I'm not going to pair them because I still have an empty orbital that's the exact same energy. Whenever possible, space out your electrons. Don't crowd them until you need to. So I'm going to put the electron in that last box all the way in the right, because now these electrons are not running into each other as often. They have space. These similarly charged things are now better spaced out because I was able to put them in different specific orbitals that had the same energies. When I get to oxygen for 8 electrons, 1s2, 2s2, do I still have room? Yes, I still have room. 2p4. And your orbital diagrams show you that you still have room. 2 in the 1s, 2 in the 2s. Now, where can I put that next electron? That next electron, I have to start pairing the electrons, but that's okay. We know 2 can fit. It's just we don't want to pair them until we absolutely have to. So there's your electron configuration and orbital diagram for oxygen. When we get up to fluorine with 9 electrons, what are we looking at? Well, is there still room in the 2p's? Yes. So 1s2, 2s2, 2p5. How's that going to look for the orbital diagram? Well, 2 in the 1s, 2 in the 2p. Where am I going to do? I'm going to have to start pairing the electrons again, but I still have room. Remember, same orbital, different spins. Different orbitals, same spins for your electrons. When I do neon with 10 electrons, do I still have room in those 2p orbitals? Yes. 1s2, 2s2, 2p6. 2 in the 1s, 2 in the 2s, and now I have all of my electrons paired up in those 2p orbitals. How do we continue? Well, we'd continue the same way we did for the quantum numbers. If you had 11, well, do I have any more room in the 2p6? No. I'd have to go to the next orbital. Well, which orbital is that? Well, there's a handy diagram that you can teach yourself how to write. I kind of have this box in here in red. Sometimes called the diagonal rule, sometimes it's called a tree diagram. What you should do is you should teach yourself how to write this diagram. Don't sit there and memorize it. When you're teaching yourself how to write it, just practice writing it over and over again such that you can quickly sketch this out without really having to think about it. What this does is this shows you the order that the orbitals get filled in. And you can see this already. And the arrows are showing you the order. The arrows always go from top right to bottom left. So if I kind of highlight what we did, what was the first orbital we used? We used the 1s. So that's what I hit. Now I try my next diagonal. My next diagonal would hit 2s. What was the next orbital we used? 2s. After 2s came what? After 2s is going to come 2p. That's the next one we use. What's going to be the next one we use? 3s. So you can teach yourself how to write this diagram, and then it's something you always have available to use really, really quickly. The next thing we're going to do is I'm going to take a much larger atom and show you how to use these diagonals in order to determine that electron configuration. So let's do an electron configuration for something that's a little bit larger. Let's do something like iodine. Iodine has 53 electrons. All you have to do is follow the pattern until you hit those 53 electrons. So iodine is 53 electrons. What do? Start filling it up. Looking over at my diagonal, what do I have? Well, first diagonal I hit is 1s. Well, that's going to be my first orbital, 1s. How many electrons can fit in the s orbitals? 2. So I'm at 1s2. What's my next orbital I hit? Well, following the diagonals, next orbital I'm going to hit is going to be 2s. Okay, so that's where my 2s comes from. Where am I going to hit or how many electrons fit in the s orbitals? 2. What's going to be my next orbital that I hit? Looking on the right tree diagram. Next orbital I hit is going to be 2p. Well, that's going to be the next orbital I'm going to fill, 2p. How many electrons can fit in the p orbitals? 6 can fit on the p orbitals. Are you at 53 electrons yet? No, nowhere close. Keep going. After 2p, what comes next on the diagonal chart? 3s. That's going to be my next orbital. 3s. How many electrons fit in the 3s? 2 electrons fit in that 3s. Now back to the right diagonal. After 3s, what's going to come next? Next diagonal, we're going to hit 3p. So 3p is my next orbital. How many electrons fit in the p's? Well, 6 of them fit in there. After 3p, what's my next orbital? Back on the diagonal on the right, 4s. What's my next orbital? 4s. How many electrons fit in the 4s? 2. Go to the next diagonal on the chart on the right. What comes next? Next I would hit 3d. So now I'm at 3d. How many electrons can fit in the d orbitals? Well, a set of d orbitals, because there are 5 specific orbitals, can hold 10 electrons. 3d10 is going to be my next piece in my electron configuration, 3d10. Are you at 53 electrons yet? No, not 53 electrons. Then you got to keep on going until you hit those 53 electrons. What comes next after 3d in the diagonal? 4p. That's going to be my next orbital I use. How many fit in the p's? Well, we said 6 end up fitting in the p's. 4p6, still not at 53. After 4p comes 5s. How many electrons fit in the s? 2. After 5s, looking on the diagonal on the right, we're looking at 4d. 4d, how many can fit in the d's? Well, d orbitals can hold, we said, 10 electrons can fit in those d orbitals, 4d10. Are we at 53 yet? No. Keep going. What comes after 4d? 5p. So 5p. We know 6 can be held there, but I'm actually already, if you would go back and count them up, 48 electrons. I only need to put 5 electrons in here for 5p5. So you can use this diagonal diagram once you teach yourself how to write this to figure out the electron configuration for any atom that you are looking at. So the electron configuration for iodine would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. You can do this for absolutely any atom out there. You're just following the pattern that you're seeing in this diagonal diagram that you can easily teach yourself to draw. You practice drawing this 5 times a day. You're going to be able to sketch it out anytime you need it, and then you just have to use it. Then it just becomes a matter of counting correctly and recognizing that 2 electrons fit in the S's, 6 in the P's, and 10 in those D's. There's a shorthand system that gets used for electron configurations. Even though it's still way, way, way better than quantum numbers, some electron configurations are very, very long. There's a shorthand that can be used. I'm not going to force you to use the shorthand, but you should be aware of it such that you understand how the shorthand works. And it works, it's called a noble gas shorthand. And what you've noticed is that noble gases will have completely filled energy levels. If you write out the electron configuration for the noble gases, what you're going to see is they have filled energy levels, meaning when you put in one more electron than what a noble gas has, you start a new energy level. So what ends up happening is when writing an electron configuration using the shorthand, you go back and start with the previous noble gas. So let's do this for iodine. The previous slide, we said iodine was 53 electrons, and we wrote out this electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. We want to write this in the shorthand. What we do is we look at the previous noble gas. So the noble gas that came before iodine, not after iodine. It's got to be the one that comes before it. The noble gas that comes before iodine is krypton. So what we do is we look at what krypton has. So I kind of highlighted how we're shorthanding this. If you were to write out the electron configuration for krypton, krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So what we do, and this is what's highlighted in the blue, we condense that down and say, okay, that was krypton. Then what we do is we just carry on with what came after, 5s2, 4d10, 5p5. So that's how you use the noble gas shorthand. All of that in blue can get condensed down into just saying it has krypton's core and then the extra stuff that comes after it. So I wanted you to see this, even though I'm not going to ever force you to write using the shorthand. When you're reading through things in the book, a lot of times they're going to be using the shorthand, so you have to at least be comfortable seeing it. There are some exceptions to the usual pattern in how we write electron configurations, and actually quite a few exceptions to the usual pattern exist. We're only going to concern ourselves with 2 of these exceptions, chromium and copper. Any other element we're going to assume follows the usual pattern. Transition elements have quite a few that are exceptions to this. Why are they exceptions? Well, they have lower energy than what just kind of our simple pattern would predict. We're only going to focus on these 2 because these 2 you can understand why these are exceptions without going through any high-level math involved in that. Some of the other exceptions, you need some high-level math to really see why you're not getting what you expect. These, you don't need that same high-level math in order to understand that. So the first one's going to be chromium. What you would expect chromium to do is you would expect, based upon the pattern, to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That's what you would expect. And this is what the orbital diagram would look like at the end. That's not what you actually get. What you actually get for chromium is you get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And if you look at this with the orbital diagram, it kind of helps show you why that ends up happening. Okay? So things are going to always go to the lowest energy state possible, whether it follows a simple pattern or not. So we want to explain why what we see is not what we would expect from the pattern. So what does it look like happen from going from the top, what we expect, to what actually happened? It kind of looked like we took an electron out of 4s and moved it up to 3d. And that's going to take energy. 4s is lower in energy than 3d. That's increasing energy. That's not what we want to do. But as a result of that electron going up in energy a little bit, the resulting system lowers the energy for everybody. The overall energy lowering resulting from all of the matching spins. Look at all these matching spins you have on the bottom. Everybody's pointed up. Everyone has that matching spin. That's going to lower the energy as well. And that end result more than makes up for the small energy investment that it takes to get the one electron from 4s to 3d. One way to think about it is think about it as an investment. Think about it as a sacrifice. That electron from 4s is going up to 3d, but as a net result of that, everybody gets a lower energy from the end result of that. So you may be thinking about this and saying, gee, well, if that happens in this case, why wouldn't that happen in a lot of other cases? And the reason it doesn't happen in a lot of other cases is there's something very specific about 4s and 3d. And if you look in the bottom left-hand figure, you're going to see that difference. If you look at where 4s and 3d are, they are very, very, very close in energy. They're almost on top of each other. So being they are so close in energy, there's only a very small energy investment you need to make, such that the return on that investment is going to lower everything else by quite a bit, because there's only a teeny tiny gap. I mean, look at this tiny gap. I'll try and highlight this in yellow. That tiny gap between 4s and 3d. You don't see that small of a gap anywhere else. If I kind of highlight one of the other gaps, 4d, 4f, or 3d, 4p, or 3p, 4s, or 3s, it's a much bigger gap. That gap's too large to get the return on that investment. So chromium is going to be one of our exceptions to this usual pattern. The next exception we're going to look at kind of follows a similar logic. The next exception we're going to look at is copper. Copper is also an exception. Copper is also an exception to the usual pattern. This results from energy stabilization from a filled set of d orbitals. So for copper, what you would expect if you were to write out that electron configuration for copper. Copper, you expect 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That's what you would expect. You see the orbital diagram on the right. What you actually get for copper is you get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Orbital diagram on the right that shows that. So you're doing something similar to what we just saw for chromium. We're taking an electron from the 4s and moving it up to the 3d. That's going to cost us a little bit of energy. So the energy lowering that we get out of that has to make up for it. So it's kind of the same thing. Look at what's really happening. From what we expect to what we actually get, it's kind of like we're taking a 4s electron and moving it to 3D. Well, where's going to be our energy investment return here? Well, it turns out if you kind of compare the two different what we expect from what we observe, what you would expect is you have the 4 S's filled, the 3Ds are almost filled. What you get is actually the opposite. The 3D is filled and the 4 S's are almost filled. It turns out filling up those 3D electrons, filling up that set, lowers the energy. That's where we're getting our energy return from. So the energy lowering resulting from completing the 3D set makes up for the small energy investment we had to take on to go from 4S to 3D. So it's the same idea that we saw for the chromium. We're taking something from 4S, moving it up into 3D, and that the end result of that gives us an overall lower energy. For chromium, what we saw previously, it was a result of all of those matching spins. That's what gave us that energy lowering. Here, it's not the matching spins, it's the ability to fill up this 3D set of electrons. And again, just like what we saw for the chromium, this can only work because there's such a small energy gap between 4S and 3D. If you look in the figure in the bottom left, I'll highlight that gap between 4S and 3D again. Very, very close to each other, almost on top of each other. Very, very small gap. Anywhere else, the gap, show this in green, is much bigger. That bigger gap means we're not going to get enough of a return out of an investment to do that anyplace else. So for our elements, the only ones you're responsible for dealing with as exceptions are chromium and copper. Every other element, you are to assume that it is following the usual pattern. But chromium and copper are going to be our two exceptions. And one of the last things we want to do with electron configurations is talk a little bit about the electron configurations of ions. Electron configurations aren't based upon an atom or an element. They're based upon the number of electrons. That's why they're called electron configurations. For ions, simply correctly count the number of electrons present, follow the pattern, and fill it up. So let's do some examples of some ions. So O2 minus. Well, oxygen has 8 electrons, but that -2 charge tells me I have 2 more electrons. That's going to mean 10 electrons. So this ion has 10 electrons. 10 electrons, fill up how 10 electrons get filled up. 1s2, 2s2, 2p6. If I look at sodium plus 1, an atom of sodium, a neutral atom of sodium, would have 11 electrons, but that plus charge is telling us it lost an electron, so it will also have 10 electrons. How do 10 electrons get filled up? 1s2, 2s2, 2p6. Magnesium plus 2, a neutral atom of magnesium would have 12 electrons, but that plus 2 charge is telling us that it lost 2 electrons to go to 10 electrons. 10 electrons, 1s2, 2s2, 2p6. N3 minus, a neutral atom of nitrogen would have 7 electrons. That -3 charge tells us I have 3 more electrons. So that would be 10 electrons. How do 10 electrons look? 1s2, 2s2, 2p6. Neon, neutral. We've done this one before. 10 electrons, 1s2, 2s2, 2p6. Have a look at what's highlighted in blue here. Notice how all of these things, and these 5 things are very different. O2 minus, Na plus, Mg2 plus, N3 minus, a neutral, neon atom. Very, very different. But they all have 10 electrons. As different as they are, the fact that they have 10 electrons means the electron configuration will be the same. because the electron configuration is based upon how many electrons you're dealing with. If you look at this, they're all the same. We have a term for this called isoelectronic. Isoelectronic means we have the same number of electrons. If you have the same number of electrons, you have to have the same electron configuration. These are sometimes referred to as an isoelectronic set or an isoelectronic series. They're all having the same number of electrons, the same electron configuration. Another thing I want to point out on this is notice the filled energy level, similar to noble gases. What do I mean by filled energy level? That means everything's filled up. If I were to put another electron onto any of these, I'd then be in the third energy level. Think about this. These all made, these ions, O2 minus, Na plus, Mg2 plus, N3 minus, all made ions of the charge that gave them that filled energy level. That's why things in the specific groups form the ions they do. If you look at O2, or oxygen's group, oxygen's in group 6A, we know things in that group form -2 ions. Why? Because they're too short of a filled energy level. Tacking on 2 more electrons will fill up the energy level. Sodium's in group 1A. Things in group 1A, we know form +1 ions. Why? Because they have 1 more electron than a filled energy level. By losing an electron, they're going to hit that filled energy level. Mg2 plus magnesium is in group 2A. We know things in group 2A like to form +2 ions. Why? Because they have 2 more than a filled energy level. By losing 2 electrons, they're going to hit that filled energy level again. Nitrogen's in group 5A. We know things in group 5A generally like to form -3 ions. Why? Because they're 3 short of a filled energy level. If you tack on 3 more electrons, you're going to fill up that energy level. That's why those are forming the ions that they do. Why are our noble gases not typically forming a lot of ions? They have that filled energy level. So now that we got a little bit more details on electron configurations, some of the things we talked about previously, the charges that get associated with each group, start to make a little bit more sense. We're able to fill in those things that you kind of just memorized before. Now you see kind of the rationale behind some of that.